Hey guys, today we're going to do section 3 of chapter 2, understanding the derivative and linear approximations. There are times when we're interested in finding the effect of small change. For example, how is the revenue at your local theater affected by a small change in the ticket price for a movie? We can explore an application of the tangent line to a function called the linear approximation. You have already seen that a curve lies very close to its tangent line near the point of tangency. If you zoom in repeatedly on the graph of f at the point a, f of a, the function will appear to be linear. When you have zoomed in to a sufficiently small neighborhood around the point of tangency, it would be difficult to distinguish the function from its tangent line. This property of differentiable functions is commonly referred to as local linearity. Now, you are looking at the graph of f of x equals sine of x. If we were to choose the point 0, 0 and zoom in 4 times, this is the graph you end up with. If we were to draw a tangent line here, that tangent line might look something like that, which is what you see here. Notice how you've zoomed in and zoomed in and zoomed in. Look at your differences here. That's 1 and that's 0.05. So quite a big difference. This is 10 and 0.61. So can you estimate the slope of this portion of the sine curve by the inspection of this window? Well, if you look at the slope, it appears to be 1. What can you say about the slope of the tangent line at x equals 0 on the function y equals sine of x? The slope of the tangent line at x equals 0 is 1 on the graph of y equals sine of x. So write the equation of the tangent line for y equals sine x at x equals 0. If the slope is 1, your graph would be the graph of y equals x. So that would be the equation of your tangent line. We're going to look at function behavior next related to the tangent line. And I will go ahead and tell you that the hardest part of this is trying to figure out the slopes based on the graphs that you see here. So what we're going to do is we're going to sketch some tangent lines. We're going to use a straight edge, and then we're going to estimate what those slopes would be. So tangent line at A, tangent line at B, and tangent line at C. And we're going to do rise over run, and we're going to estimate the best that we can. So rise over run 1, 2, 3, 4, maybe 5. It's pretty steep. Maximums and minimums are the easiest because their slopes are 0. That one's positive, so this one's going to be negative. It looks like -2. Again, these are approximations. Now, we have a graph here that appears to be an absolute value function, and notice this function comes to a sharp point. Slopes do not exist at sharp points. Because they're slopes. There's not a slope of 0 there because there's no curve. It's just a sharp point. So there is not going to be a slope there. Because the sides of an absolute value function look like lines, we would just trace them to find their tangent lines. So 1, 2, this one's -2 and +2. So notice we are declining negative slope and then inclining positive slope. Part C is very similar to Part B. Our slope does not exist here at Part B. This is called a cusp. Cusp have more of a curve before they come to the sharp point, as opposed to the line segments that come to a sharp point. So we're going to draw our tangent lines at A and C. And the best that we can, we're going to find our slopes by counting rise over run. This one is about -1/2. Excuse me. And this one is about +1/2. They look the same, so you would expect that their slopes would be the same, except one is declining, so it would be negative. The other is inclining, so it would be positive. If we were to draw a tangent line here, it would be vertical. So we are approaching the tangent line from the left and from the right. Vertical tangent line will not exist for a slope. Remember, the slopes of vertical lines do not exist anyway. For example number 3, the position of the tangent line relative to the function it models depends on the concavity of the function at the point of tangency. Concavity is changing like from concave up to concave down. So if you had a function that looks like this appears to be opening up and then appears to be opening down. So your concavity change would be right there in the middle. Throughout the course, you'll be required to explain, justify, and defend your knowledge using proper terminology and precision. Use the graphs from example 2 above to complete the following statements. So when the curve is concave up, the tangent line, we'll just draw an example here, would be below the curve. So think about the next one. When the curve is concave down, the tangent line lies concave down, tangent line lies above the curve. Notice for both of these, this is except at the point of tangency. At a maximum or a minimum, let's do minimum. Point of tangency would be the tangent would be horizontal with a 0 slope. And at a concavity change, like part D, at a point of inflection, concavity changes, the tangent is going to be vertical. Or in some instances, it could be 0. At a sharp corner or cusp, the tangent, looking at B and C, does not exist. And at a point on a linear function, like part B, the tangent is the same slope as the line. Make sure whatever questions you have that you mark them in some way so that we can get back to them easily. Example 4. Consider the radical function y equals the square root of x. Use the difference quotient to find the slope of the curve at x equals 9. Difference quotient. So the limit as x approaches 9, f of x minus f of a over x minus a. Rationalize because direct substitution will not work. Square root of 9 is 3. So square root of x plus 3, square root of x plus 3. The limit as x approaches 9, of x minus 9 over x minus 9 square root of x plus 3. And what we want to happen is happening. The x minus 9's cancel. We're left with 1 on the top. We're going to substitute 9 in for x. 1 over the square root of 9 plus 3 is 1 over 6. Write the equation for the linear approximation of f near x equals 9. That's going to be your tangent line. So we know that if we plug 9 in, if x is 9, square root of 9 is 3. So our point, 9, 3. And our slope is 1/6. Y equals m times x minus x sub 1 plus y sub 1. Use the equation in part B to estimate the value for the square root of 9.1. Do not use a calculator and show your work. You're going to find from time to time, you're going to have to use some real basic math to answer some questions, and it might take you a little while. So just make sure to try to keep your careless mistakes to a minimum. So f of 9.1 is going to be 1/6 times 9.1 minus 9 plus 3. And some of y'all are looking at that and you're saying fractions and decimals in the same problem. I'm not sure if I can do this. You can, just might be some review for you. Simplify 1/6 times 0.1 plus 3. And we'll change this 0.1 to be a fraction to match my 1/6. So 1/6 times 1/10 plus 3. I'm going way back to mixed numbers. This is 1/60th. Plus 3 is 3 and 1/60th, which transforms to be 181 over 60. And now we're going to do some basic division. And I know it's not going to go evenly, so I know I'm going to need probably a couple zeros after that. So 60 doesn't go into 18, but it goes into 181 3 times. Bring down your 1 and your 0. 60 does not go into 10, but it will go into 100 one time. Bring down another 0. 60 goes into 400 6 times. And there's another 40 for another 400, so that 6 is going to repeat. So f of 9.1 is going to be approximately 3.016 repeating. And if you are working on a particular assignment where calculators are not allowed, that's what you're going to be expected to do. Graph the function and its tangent at the line x equals 9. So y equals the square root of x. This one's actually pretty easy to graph. 0, 0, 1, 1. Square root of 4 is 2. Square root of 9 is 3. Square root of 16 is 4. You guys should know this is the parent function for the square root, and you should know what that graph looks like. And now we're going to draw the tangent line when x equals 9. And this will be at the point 93. Explain whether your answer to part C is an overestimate or an underestimate for the actual value of the square root of 9.1. Justify your answer by reference to the behavior of the graph of f of x. Well, we just talked about this on the last page. This graph is concave down. So the estimate is an over approximation because your tangent line is on top of your curve. So f of x is concave down. So the estimate is an over approximation because the tangent line lies above the function. Now, notice you have a calculator here that lets you know you're going to need your calculator to do this problem. Find the true value of the square root of 9.1, and look how close that is. 3.016620.626. Now that is obviously still an approximation because there might be a million digits beyond that, and your calculator is not going to show all that. So would your linear approximation formula, the formula that we found in Part B, be an accurate tool to estimate the square root of 25? Why or why not? I hope that's an immediate answer for you. We're looking for something around the square root of 9.1, which is 3. The square root of 25 is 5. So this is no. The square root of 25 is too far away from the point of tangency. And using the terminology that they used a while ago, it is outside the local neighborhood. So that gives you kind of an illustration of what that meant when they put that in the paragraph. All right, for example 5, you're going to want some colored pens or some colored pencils, whichever works best for you. We are going to fill in our chart based on the graph like we did before. Use the graph of the continuous function y equals g of x shown below to complete the table. We know the derivative of a function at a point represents the slope of the tangent line at that point. Estimate the value of g prime of x for each x value in the table by drawing a tangent line through the given point of tangency and estimate the slope or derivative at the point. Find the y-coordinate of the point of tangency and use the point-slope form of an equation to write the equation of the tangent line at the point x equals a for each x value. Remember your tangent line approximation formula here. That would be your slope times x minus x of 1 plus y sub 1. All right, at when x is negative 3. 1, 2, 3. All right, so A is going to be our point that we're concentrating on there. This is a steep declining slope. So we're going to estimate that. 1, 2, 3, 4, 5, almost 6, negative 6. The point of tangency is negative 3, negative 3. You are decreasing, which you can see by the graph. So your equation, y equals negative 6 times x plus 3 minus 3. Again, the hardest part is when you're not on a grid, so to speak, finding that derivative estimate, which is your slope of the tangent line. All right, when x is negative 2, we're looking at part B, or point B. This one's easy. We're at a minimum, so our slope is 0. It is the point negative 2, 1, 2, 3, 4, 5, 6. Because your slope is 0, it is constant. And y equals negative 6. Remember, a 0 slope is a y equals equation. Y equals a number. Negative 1/2 is going to be C. And it looks like, let's see. Look out, 3. Negative 1/2, negative 2. Your graph is increasing. y equals 3 times x plus 1/2 minus 2. 1.25, again, this time you are at a maximum. So you have a slope of 0, which means you're constant. You are at 1.251. So y equals 1 would be your equation. And when x is 4, 1, 2, 3, 4, we are at g. Pretty steep slope here. We need to extend that a little bit more so we can count. Let's see. About 7. Point of tangency 4, 3. Your graph is increasing. So y equals 7 times x minus 4 plus 3. And when you have a problem like this that's on an assignment or on an assessment, I will make sure that you can clearly see where your points are so that you can clearly find your slope. All right, we're going to look at slope graphs or f prime graphs next. When you plot the motion of an object as velocity versus time, these are referred to as slope functions or f prime graphs. In the study of calculus and physics, these graphs represent the rate of change of the original function. By analyzing these graphs, you can find where changes are occurring slowly or quickly by observing the rates of change or slopes of the tangent lines at specific moments in time. Consider the function shown below. Notice the curve at the first point, x equals 1/2, right here. The slope of the curve here appears to be about 1. Then at x equals 4, the slope has decreased to about 1/3. So we're going to analyze and sketch the slope graph on the grid below. So we know we're decreasing, so our graph is going to be going down. The reason it's going down is because we've gone from a slope of 1 to a slope of 1/3, and that is a decrease. So that means your graph is going to go down. So you know when x is 0.5, f prime is 1. So this is going to be the point 1/2, 1 on our derivative graph. So this is going to be our next point, 0.51. And then when x is 4, f prime is 1/3. So this will be the point 4, 1/3. And we know that this is a curve. So that means our graph here is going to be a curve. And the only way we can have a curve is for us to come down here and connect those dots. So this is our f prime graph. And we're graphing it with the slopes from the tangent lines from graph 1. Now we're going to compare the graphs of f to f prime. First thing that points out to me is we have a slope of 0 and a slope of 0. Now, how that transfers to our f prime graph is these x values are my x-intercepts. So this occurs at -1, and this occurs slightly past 4. We have a point of inflection because we're going from concave down to concave up. So we have a point of inflection somewhere in here. And that point of inflection becomes your minimum value here. So we are concave down from negative infinity to negative 1.5, and we are concave up from 1.5 to infinity. And notice that's about where your minimum is here. So the f prime graph gives us insight into the behavior of the original function. For example, at x equals 1, the slope on y equals f of x appears to be almost negative 2. Therefore, on the graph of y prime, the value at 1 is almost negative 2. 1, almost negative 2. There are several relationships between the two graphs that are particularly important to note. So let's look at that. F prime of, we'll say negative 0.9 because it's almost 1, is equal to 0. Slope is 0, which is also equal to f prime at, we'll say a little past 4, 4.2. So these are the x-intercepts on the f prime of x graph. When the graph of a function is rising, we will say that the function increases. When the graph is falling, we will say that the graph decreases. It is customary to read a graph in much the same way as we read a book, from left to right. So all of that information is important. Starting at the left on the graph of y equals f of x, state the intervals of x where the graph rises. What do you notice about the slope of the curve on these intervals? So we're looking at the graph of f. Where does it rise? Well, it's increasing, hits a point, then it decreases, hits a point, and then it increases. So the first question is, where does it increase? So it increases from negative infinity to negative 0.9 and from 4.2 to infinity. So f of x increases on the interval from negative infinity to negative 0.9 and x greater than 4.2. It's increasing because the slope of the curve is positive here. Analyzing that same graph, where does the graph fall and what is the slope of the curve? So it falls, decreases, on the interval negative 0.9 to 4.2. The slope of the curve is negative here. At what values of x on the graph of y equals f of x does the function appear to have a maximum or minimum value? What is the slope of the curve at these points, and what characteristic of the f prime graph occurs at these points? So quite a few things we have to answer here. We have a relative maximum here and a relative minimum here. That's where we're going to start. So f of x has a relative maximum at x equals negative 0.9 and a relative minimum at x equals 4.2. The slope of the curve is 0 at these points. So on the graph of f prime, of x equals negative 0.9, and x equals 4.2 are x-intercepts. All right, part D. Now look carefully. Why does the graph of f prime reach a minimum value near x equals 1.5? Can you explain what is occurring at x equals 1.5 on the graph of f to create this minimum on the slope graph? So why do we have a minimum here? Because of our change in concavity, our point of inflection on the graph of f. So at x equals 1.5 on f of x, the graph changes from concave down to concave up, which is a point of inflection. So what happens if you have to create your own graph? So there is a procedure to sketch an f prime of x slope graph from y equals f of x. Describe how the slope changes from left to right along the curve. Notice the intervals where the slope is positive, negative, and 0. Write down the changes as they occur from left to right on a number line. Notice where the x-intercepts occur. Pay attention to where the function is above the x-axis, where it's positive, and where it is below the x-axis, which is where it will be negative. And now we're going to do some sketching here. You might want some different colors to make it kind of clear as to what is taking place where. All right, so on the graph of y equals g of x, the first thing I will notice is I have a slope of 0, and that's at x equals negative 2. And then I have a slope of 0, and that's past 3. So we're going to say x equals about 3.3. Again, we're estimating. So that's what's going down here on my number line. So I've got g, and what's that going to look like on g prime? So I have a slope of 0 at negative 2 and a slope of 0 at 3.3. So we're going to make a note there. These are the slopes because the graph has a max or a min. So you can see where these numbers are coming from. So what's happening to your graph? Well, we read it from left to right like a book. So we are decreasing, which means we're going down. From negative 2 to 3.3, we are increasing. So we're going up. And from 3.3 to infinity, we are decreasing. So we're going down. So what does that mean on G prime? Well, taking a look back at the G graph, we're going from concave up to concave down, somewhere right in here. So we're going to say that's around 0.8. So we have a point of inflection at 0.8. That means on my G prime graph at 0.8, I'm going to have a maximum. And I'm going to show you why it's a maximum here. Our graph starts by opening up, so concave up, which is an indication you are increasing. And then we switch and we go to concave down, which means we are decreasing. So when you are increasing and then decreasing, you have a max or a maximum. So that maximum, the point, is going to be approximately what our slope would be. So it's kind of steep, so about 2. So 0.82. And then at -2, we have an x-intercept. And at 3.3, we have an x-intercept. And then we connect our dots for our graph of G prime. Now, one extra thing we want to add here, at this point, G double prime of x would be 0. Mark the number line above to show values where y equals g of x changes from increasing to decreasing. At these x values, the slope of the curve is 0. We've already done this, so we're just filling in our blanks. On the function, we refer to those values as extrema, or a maximum, or a minimum. Notice how the graph of g of x changes from concave up to concave down. Estimate the x value where this occurs and place this value on the number line to the right as our -0.8. You will see that this will become either a maximum or minimum value on the graph of the derivative g prime. This value is commonly known as point of inflection. We've gone over all that. And then we have created the value of our derivative, or excuse me, the graph of our derivative. Next, we're moving to derivatives from a table. You are going to be using your basic slope formula here. And by that, I mean the one that you used in your Math 1 class. All right, so we want to find the slope at -2. So if we want to find the slope at -2, we're going to use the two values of f of x and the two values of x on each side of -2. So f prime of -2 equals -6 minus 4 y1, or y2 minus y1 over x2 minus x1, -4 minus -1. -10 over -3 is positive 10/3. Because it is positive, you are increasing. So at -2, 2, f prime of -2 is greater than 0. All of these are like that. So if you would like to pause and do these yourself, you are welcome to do so and then come back and check. -1 on each side. So f prime of -1 equals 2 minus -1 over -2 minus 0. 3 over -2, -3/2 means you are decreasing. So at the point -1, 4, f prime of -1 is less than 0. At 0, 4 minus 4 over -1 minus 2 is 0, so you are constant. So at 0, -1, f prime of 0 equals 0. This is a relative minimum because f of x goes from decreasing 4 to -1 to increasing -1 to 4. And if you were to plot that, -1, 4, 0, -1, 2, 4, you would clearly see that minimum. All right, f prime of 2, -1 minus 2 over 0 minus 3. 3 over 3 is 1. You are increasing. At the point 2, 4, f prime of 2 is greater than 0. And the last one, f prime of 3 4 minus 0 over 2 minus 8. 4 over negative 6, so negative 2/3. You are decreasing. So at the point 3, 2, f prime of 3 is less than 0. Now, one quick thing about this before we head into the last part. You are increasing. And the way that you can tell that you are increasing is because at negative 2, if you look at each side, you're going from negative 6 to 4. That's an increase. At negative 1, you're going from 2 to negative 1, so it's a decrease. At 0, you're going from 4 to 4, so it's staying the same. Remember, these are slopes. So at 2, you're going from negative 1 to 2, which is an increase. And at 3, you're going from 4 to 0, which is a decrease. So you're just justifying what's already in your chart. So if f prime of x is less than 0, then the graph of the function is decreasing at x equals a. And if f prime of x is greater than 0, the graph of the function is increasing at x equals a. A relative maximum occurs on a function if the slope, which is the derivative, is 0, and the derivative changes. Maximum. Think of maximum. So you're increasing positive to negative. So if you're doing a minimum, you're decreasing to increasing. So your slope is 0, and you are going from negative to positive. All right, this concludes section 3. As always, let me know if you guys have any questions, and I'll talk to you soon.